The last part of looking at implicit derivatives is looking at what happens when you actually have to do the process twice. You would never do it more than twice. I know we know how to do lots of different levels of derivatives, but twice can add some interesting challenges. So I want to take you through this. So we're going to start with something really simple, and that's one thing you're going to notice when you are asked to do a second derivative with an implicit function. They're going to start with a very basic initial function. So I'm going to derive x squared plus y squared equals 25. I get 2x plus 2y dy dx equals 0. And then I'm going to subtract 2x. So I get 2y dy dx equals negative 2x. And then I'm going to divide by 2y. And I often mention that I don't care if you simplify or not. I will say, because we have to go further, if you can simplify anything, it's in your best interest just because it makes things easier. So I'm going to cancel those 2's and write the derivative as negative x over y. So now I need to derive again. So I'm going to kind of do it in this upper column here. When I derive again, so when I look at the left side and I have dy dx, when I derive a second time, I'm going to get d squared y dx squared. Now when I derive this side, a couple things that you'll notice. First of all, it's still implicit, so you're going to have to do an implicit differentiation again. The other thing you're going to realize is more often than not, it's going to be a quotient rule because you do have a numerator and a denominator. So when I derive that, I'm just going to treat the negative as part of the x. I'm going to kind of lump it together with that. So I'm going to do bottom times the derivative of the top minus the top times the derivative of the bottom. Derivative of y is dy dx, all over the bottom squared. And I've got some messy negatives, so I'm just going to kind of clean it up just a little bit and write it like that. Well, here is the issue, and this is what a lot of students miss. I've seen these show up on like free response questions, and if a student got to this point, they would give them all the points except for one. And here's the one that we need. Your answer should be only in terms of x's and y's. And right now, your answer is still in terms of x's, y's, and this random dy dx in there. We have to be able to replace that. Here's where this comes in. We know what dy dx is, so we can actually make that a replacement right away. When I'm going to replace dy dx, I'm going to put what I found earlier in the problem, dy dx, to be. Sometimes they'll actually do the first derivative for you, so they have to give you that information, or they'll make you do it yourself. So here now, and it's not simplified, and that's totally fine. It doesn't have to be simplified, but this is my equation for my second derivative done implicitly. So you're going to do the first derivative. You're then going to do the second derivative, often with the quotient rule, and then you need to remember to replace your dy dx with what you found it to be earlier in the problem. So let me show you another one. Again, we're starting with a really simple equation, y squared equals x cubed. So my derivative, my first derivative implicitly will be 2y dy dx equals 3x squared. I'm going to divide by 2y. So my first derivative is actually done very quickly on this one. So that's derivative number 1. To do the second derivative, I'm going to come up again in like a second column. I need a quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be a 2 dy dx, all over the bottom squared. You can square it out if you want. Again, I'm going to clean it up a little bit. So I'm going to take my 2y times 6x and write it as 12xy. Minus, I have 3x squared times 2, 6x squared. I'm also going to replace the dy dx while I'm at it. I know my dy dx is 3x squared over 2y over 4y squared. And I'm really not going to get into a lot of extra simplifying because I don't have anything further to do with this question. So that's looking at that second derivative. So there are questions that they'll ask you to do a second derivative, but they'll give you a numeric value. In some ways, these are slightly easier. So I want to show you some kind of helpful tips and shortcuts with these. So this is what you'll be given. I took this one from Delta Math. You probably recognize the font, where they're asking you to find the second derivatives and put in this value. When they say simplest form, they just mean reduced fraction if you can, or decimal. I usually put things in reduced fractions. So my derivative is 3 dy dx plus 2y dy dx plus 4x equals 0. So I'm going to move the 4x. So I have a negative 4x. I'm going to pull out the dy dx on the left side. So I have 3 plus 2y. And I'm going to divide. Again, you tend to end up with first derivatives that aren't too bad. You don't see very many product rules or things like that. So my second derivative, it will involve a quotient rule again. So bottom times the derivative of the top, which is negative 4, minus the top times the derivative of the bottom. The derivative of the bottom is going to be 2 dy dx all over the bottom squared. So when it comes to cleaning this up, let me show you some things that I have felt have helped me. So you want to put a 1 in for all your x's and a negative 2 in for all your y's, and you realize you also have this dy dx. So here's the best thing to do with this. See what dy dx equals at 1, negative 2. So put that into here so you can get a numeric value. Then you can just plug that numeric value in. So when I put 1, negative 2 in, I get negative 4 over 3 plus 2 times negative 2 is negative 4. So I get negative 4 over negative 1. So I get 4. And that's going to help me replace that with just a number value rather than a larger expression. So I've got 3 plus 2 times y, so that's negative 4, times negative 4, minus a minus, so I'm just going to change that to a plus. 4 times 1 is 4, times 2 times another 4, and that 4 came from the dy dx, over 3 plus 2 times negative 2, so 3 plus negative 4 squared. All right, so what do we end up with here? We get negative 1 times negative 4 is 4, plus 4 times 4 times 2 is 32, all over negative 1 squared, which is 1. So lots of work to get to a single numeric answer, which is the second derivative at that value. I'm going to take you through one more in case you feel like you need it. Same idea. Sometimes it just takes one more try. This one does have a messier first derivative. So I'm going to do a product rule. So first times the derivative of the second plus second times the derivative of the first, which is just going to be negative y, equals 0 would be the derivative of 3, and then minus 3 dy dx. So let's see. Let's bring this over here and this over here. So I have a negative x dy dx plus a 3 dy dx equals y. And then I'm going to factor out a dy dx, which is negative x plus 3. And then I'm going to divide both sides by that. Or you could write it as 3 minus x if you want. So that's my first derivative. So my second derivative, again, it's a quotient rule. Pretty much all of them are. So bottom, which is negative x plus 3, times the derivative of the top, dy dx, minus the top times the derivative of the bottom, all over the bottom squared. So I want to put in 4, negative 3. So the first thing I'm going to do is I'm going to put it into the first derivative so I know how to replace that. So when I put negative 3 on top and then I put a 4 on the bottom, I get negative 3 over negative 1, which is 3. So that tells me how to replace my dy dx. It is much easier if you can get it down to just a single number. So then I'm going to put everything else in. So I get negative 4 plus 3 times 3. Minus a minus would be plus y, which is negative 3, all over negative 4 plus 3 squared. So in my numerator, I get negative 1 times 3 is negative 3 plus another negative 3 over negative 1 squared, which is 1. So my answer is negative 6. So that is how sometimes they'll do that to kind of get you away from doing a lot of algebra simplifying. So instead of really simplifying and cleaning up the x's and y's, you're just immediately plugging in a given x and y to go to a numeric answer.